Assalamu alaikum. This is Naima Khan. Today I am going to talk about one of the most fascinating and complex areas of defense and aerospace engineering, which is the missile technology. We will explore how material science, chemistry, artificial intelligence, and manufacturing techniques all come together to build these powerful systems. Let us see about which we will talk in this presentation. This presentation delves into intricate world of modern missile technology, exploring the foundational scientific and engineering principles that enable these complex systems. From the advanced materials used in their construction to the sophisticated AI that guides them, we will uncover the multidisciplinary nature of missile development. Let's move toward the introduction of the missile technology. Missiles are highly integrated systems. They bring together advanced materials, explosive chemistry, precision propulsion, and cutting edge AI guidance. They are used in defense, space exploration, and maintaining strategic deterrence. Each use case demands different capabilities. Major structure components of a missile. A missile is made of four main sections. First one is nose cone, also known as warhead section. This houses the warhead and guidance sensor. Second one is guidance and control. It ensures the missile follows its intended path using GPS, sensors, and flight computers, etc. Third one is propulsion section. It provides thrust using solid, liquid, or air breathing engines like scramjets. Fourth one is tail section. It maintains stability using fins and nozzles for steering. This is the basic structure of a missile. Missile materials must handle extreme forces and heat. Aluminium 7075T6 is a strong and light used in the fuselage. Fuselage is basically the main body of a missile. Titanium 6Al4V handles high temperature, ideal for hypersonic flight. Carbon-carbon composites resist over 2000 degrees Celsius. These are perfect for re-entry vehicles. Ceramic matrix composites protect scramjet engines. Each component from the warhead casing the nozzle uses carefully chosen materials based on their properties. Advanced materials are critical for missile performance, especially under extreme conditions. As I told you earlier, aluminium 7075T6 provides an excellent strength to weight ratio for general airframes. For high speed and hypersonic applications, titanium 6Al4V is favored due to superior heat resistance. For spacecraft and re-entry vehicles, carbon-carbon composites are indispensable for the ability to withstand temperature exceeding 2000 degrees Celsius. Similarly, ceramic matrix composites offer crucial thermal protection for advanced propulsion systems like scramjets. Propellant casings also rely on advanced materials. Filament-wound Kevlar or graphite epoxy provides high tensile strength, while specialized steel alloys like marine steel are used for the robust motor casings of intercontinental ballistic missiles. This is an basic overview of the components of a missile and the materials used in these components and reason for the selection of these components. Missiles depend upon various subsystems: aerodynamics, wings and fins, control movement. Second one is avionics and electronics, computers and sensors, process navigation and targeting. The power systems, thermal batteries or ram air turbines keep everything running. Warhead mechanisms, different fuses control when and how the warhead detonates. Let's talk about the propulsion chemistry. There are two main types of propellants: solid propellants and liquid propellants. Solid propellants are simple and reliable. They mix fuel like aluminium with oxidizers like ammonium perchlorate. Here is a combustion reaction where ammonium perchlorate is oxidized with aluminium and form alumina with nitrogen and HCl with the release of energy and water. Liquid propellants offer more control. Hypergolic fuels like UDMH and N2O4 ignite on contact. Cryogenic fuels like liquid hydrogen and oxygen offer more thrust but require careful storage. There is a hypergolic reaction in which N2H4 and N2O4 reacts and form nitrogen, water with the release of energy. Warhead explosives. Missiles use various explosives depending on the mission. RDX and HMX, high energy compounds used in the traditional warheads. CL-20, one of the most powerful known explosives. In nuclear warheads, a fusion stage ignites a fusion stage, producing massive energy in a compact form. Conventional high explosives are carefully engineered for specific applications in conventional warheads. While nuclear warheads typically implies two-stage design, the primary stage involves a fission reaction, often using a plutonium-239 implosion designed to generate a powerful initial blast. This energy then triggers the second stage, which utilizes lithium deuteride in a fusion reaction to achieve a much larger thermonuclear yield. This sophisticated process maximizes destructive potential with a compact design. AI and software missiles. Artificial intelligence is transforming missile guidance. Neural networks help with real-time target recognition. Reinforcement learning allows missiles to dodge defenses. AI also helps in cyber warfare like GPS spoofing or jamming enemy systems. Swarm missiles use decentralized AI, meaning no single failure can bring down to the group. Fabrication techniques. Modern fabrication is all about precision and speed. 3D printing allows rapid prototyping and complex internal structures. CNC machining is used for precision parts like sensor housing, explosive forming shapes, large or complex metal parts using controlled detonation. Future structure advances. The future of missile is even more high-tech. 3D printed bodies make production faster and lighter. Morphing wings can adjust shape mid-flight. Self-healing materials extend missile life and reliability. AI-optimized structures can design themselves to be more efficient. This bar graph compares ballistic missiles, cruise missiles, and hypersonic missiles in terms of four structure aspects, which is structure, propulsion, guidance, and trajectory. Here is a breakdown in simpler terms. In the structure one, the ballistic missiles have a relatively simple structure. Cruise missiles are more complex than ballistic ones as they resemble small pilotless aircraft, while the hypersonic missiles are most advanced due to extreme speed and heat resistant requirements. In terms of propulsion, ballistic missiles use basic rocket engines that boost them early in flight. Cruise missiles use jet engines for sustained low altitude flight. Hypersonic missiles use cutting edge propulsion like scramjets, making them fastest among the three. In the guidance, ballistic missiles are minimal in flight guidance, mostly follow a fixed arc. Cruise missiles steer themselves in real time using GPS and sensors. Hypersonic missiles are highly responsive throughout the flight. In the trajectory, ballistic missiles follow a high arcing, predictable path. Cruise missiles fly at low altitude, avoiding detection. while the hypersonic missiles have unpredictable dynamic flight paths that are hard to track or intercept. So, in the summary, the hypersonic missile ranks highest across all categories due to its advanced tech and performance. While ballistic missiles tend to the most straightforward, cruise missiles offer a balanced mix of complexity and maneuverability. To wrap up, missile technology is perfect fusion of science, engineering, and AI. Looking ahead, hypersonics, AI, autonomy, and advanced manufacturing will define the next generation. But as missiles become more intelligent, we must also address ethical questions, especially around autonomy, and global security. Thank you for your attention. I hope this presentation gave you a deeper understanding of how multiple disciplines come together to create one of the most advanced technologies in the world, missiles. Thank you. Allah Hafiz.